We introduced the Compton effect just before our unit test. We said the Compton effect is somewhat like the photoelectric effect. Light strikes a piece of metal, an electron is sometimes ejected. The Compton effect, though, says if you have a really high energy photon, we're talking about something like an X-ray, right? Really high frequency, therefore really, really high energy. Then not only do we get an electron ejected, sometimes we actually get a photon ejected as well. So you've got a photon strikes a metal, electron and a photon are ejected. Now, classical theory, old style physics, would have predicted that that second photon would have been the same photon as what we started with. So if the first photon was an X-ray, then the second photon would be an X-ray with the same frequency. You just get an electron produced in the process. But that's not the observations. That doesn't match with the observations that were made. We observed prior to 1908 that second photon would be less energetic than the first photon. In other words, it would have a smaller frequency than the second photon. Okay, nobody could really explain why until Compton came along. Compton said that when you got a collision, when you got this interaction between the photon and the metal, and you got a second photon and an electron ejected, it's really just a collision. It's really just like a car going through a stop sign hitting another car. It's really just a conservation of momentum problem. But everybody looked at him and said, you're crazy because photons can't have momentum. Photons can't have momentum because they don't have any mass. They've got energy, right? E is equal to h times f, but they don't have any mass. And you can't have momentum if you don't have any mass. Well, Compton said you can. Compton said you can have momentum when you don't have mass because he went back to what Einstein said in 1905. Einstein said that energy and mass are really two different forms of the same thing, kind of like ice and steam are two different forms of the same thing. We can change ice to steam and steam to ice. We can change energy to matter and matter to energy. So although we don't have any mass to give this photon momentum, we do have energy. And energy is like the same thing, another form of mass. We'll derive those equations again in just a second here. Two little terms here, the scattering of the photon that gets scattered, so the high energy photon that gets scattered into a smaller energy photon or smaller frequency photon, we call it Compton scattering. The change in the energy of the photon, if the decrease in the energy of the photon is called the Compton effect. Now, we derived a couple equations on Monday before the test here. We started off with the equation P is equal to m times v. That's the momentum of anything, right? The momentum of a car or of a baseball or of an electron or a proton. The equation that we learned on the very first day of Physics 30 at the end of January. That should apply to photons as well, except that photons don't have any mass. Well, then we introduced this other equation that Nick was so excited to see for the first time. Einstein's energy mass equivalence equation, E is equal to mc squared. This one says that energy is equal to this much mass times c squared. In other words, if you got a certain amount of mass, this is how much energy it's worth. This is how much energy it's equivalent to. It's kind of like saying, this is ice, this is steam. You got this much ice, how much steam is it equivalent to? Okay, this much mass, how much energy is it equivalent to? Well, let's rearrange it, because we don't have mass trying to find the equivalent energy. We have energy trying to find the equivalent mass. So m is equal to E over c squared. This is the energy of the photon. This is the speed of light squared. Okay, this is the equivalent mass. Don't have that much mass, but it's like we have that much mass. Just like we don't have that much ice, but it's like we have that much ice. So let's sub this in here. We end up with E over c squared times v. But v, we're talking about a photon here, so v is the speed of light. We'll change it to the symbol c. Let's cross off one of the c's, cancel them out. And we're left with P is equal to E over c. Now on your data sheet, you see that equation. It's phrased a little bit differently. It's rearranged to take the form E is equal to P times c. But it's the same equation. The energy of a photon is equal to the momentum of a photon times the speed of light, 3 times 10 to the 8 meters per second. For the first time, we've now got an equation that describes the momentum of a photon. It relates it to the energy of that photon. Now, you will also see in the top right-hand corner of your data sheet another equation that's a lot like this. If we take this one, P is equal to E over C, and replace E with H times F, because the energy of a photon is H times the frequency, then we're going to get this one. HF over C. If you replace E with HC over lambda, which we can do because energy is equal to HC over lambda, then we get this equation. Looks a little odd, so let's simplify it a little bit. We end up with P is equal to H over lambda. These three equations all describe for us the momentum of a photon, the momentum of a particle of light, the momentum of something that doesn't have any mass. Now, if we're asked to go back to Unit 1 and find the momentum of a car or the momentum of a proton or an electron, what are we going to use? One of these equations? Well, not necessarily conservation of momentum, right? If we're asked to find the momentum of a proton, we'll simply go back to that very first equation that we learned for momentum, P is equal to m times v. So these three equations in blue here, the momentum of a photon, the momentum of something without mass, the momentum of a particle of light, a quantum of energy. The red one, still use that, but here we're talking about the momentum of something with mass. Okay, don't get those mixed up. All four for momentum, only one of them is the momentum of a particle with mass. Three of them are the momentum of photons. Got it? Well, here's another equation. This one describes for us the change in wavelength of the photon. We know there's going to be a change in wavelength, right? If there's a change in energy, there's going to be a change in wavelength, change in frequency and change in wavelength. Well, the first part of this equation is pretty straightforward. Delta lambda is equal to lambda f minus lambda I. So whatever the wavelength of the photon is after the interaction, subtract whatever it was before the interaction. The bottom part is a tricky one. This is the ugly part. H over m times c times 1 minus cosine theta. It looks pretty ugly, actually. But it's not so bad when you go to actually solve it, as long as you know what each of the variables mean. Let's take a look at that. H stands for Planck's constant. What value do you think you should use here? Let's use joules. Always use joules. So now we've got a third situation where we've got to use joules, right? QV, 1 FmV squared, and this whole delta lambda equation. We've got to use the 6.63 value. Six 6.63 times 10 to the minus 34 joule seconds. Now m, that stands to reason that's going to be a mass, right? What mass are we going to use here? The equivalent energy? No. Good guess. If that was the case, we'd probably just throw in an E there, right? An energy or some kind of equivalent energy. What is it that actually has mass in this whole deal? The electron. So let's use the mass of the electron. 9.11 times 10 to the minus 31 kilograms. C stands for the speed of light, 3.00 times 10 to the 8 meters per second. I've often wondered why they don't just give us a single constant for this coefficient out front, h over mc. It's always the same three numbers. It's always the same three numbers. So why don't we just turn that into one number, one constant? Unfortunately, they don't. Okay. Now, you could figure out what that number is. The only problem is that number is not going to be on your data sheet. So probably might as well just stick with what we got there. Okay, h over mc times 1 minus cosine theta. What do you think theta stands for? It's an angle, right? Clearly it's an angle in degrees. But what angle? Yeah. No, but you're close. It's a scattering angle, but not the scattering angle of the electron. It's a scattering angle of the photon. Be really, really careful with that. Scattering angle of the photon versus the scattering angle of the electron. I've seen a question, I can't remember how many years ago I saw this, it might have been 2 or 3 years ago on an exam, that basically asked you to identify what theta is. Okay, and one of the options, of course, was the scattering angle of the photon. One of the options was scattering angle of the electron, right? And that's such an easy one to get mixed up on, it really is. Now, if you get a mathematical question, I'd be shocked if they give you the angle of the electron and the photon. I don't think you'll get confused there, because I think they'll just give you the scattering angle of the photon. Okay, but if they ask it to you in terms of, do you know what this means, then they might ask that. So be really careful on that. All right. So we got 3 new equations on this page, circled in blue here, that all relate the energy of the photon, or the frequency of the photon, or the wavelength of the photon to the momentum. And then we've got this new equation that talks about the wavelength, or the change in wavelength. Hey, quick question before we do an example here. What's going to happen to the wavelength of this photon? Is it going to increase or decrease? You're going to have a higher wavelength or a smaller wavelength? Who says higher? I heard a couple of people say higher. I heard a couple of people say lower. Who says lower? Okay. One person says both, higher and lower. It's going to be a higher wavelength. The wavelength is going to increase. How is that possible? How are we going to increase the wavelength? Yeah. No, the frequency is not going to go up. Frequency is going to go down. Frequency goes down because the energy goes down, right? If the energy goes down, the frequency goes down, and the wavelength goes up. So you're always going to get a positive delta lambda there when you're solving that. All right. Let's take a look at this example that's not in your textbook, unfortunately, so I'll ask you to just quickly copy that one down. It says calculate the energy and the momentum of a photon whose wavelength is 600 nanometers. Right. So that's our wavelength here. Once again, we see this for the millionth time, the fact that wavelength is given to us in nanometers. Okay, be prepared for that, because we see that a lot, right? Basically, when you're talking about something that's hundreds of nanometers, you're talking about visible light, and that's usually what we're dealing with. We want to find the energy of that photon, and we want to find the momentum of that photon. Now, be careful, you don't go and use P is equal to m times v. Now, you can, I suppose, use P is equal to m times v, as long as you derive the equation that you need to use from that. Okay, what I would suggest you do is go to your data sheet and just take it right from your data sheet. We've got the wavelength. The momentum can be found by P is equal to h over lambda. We're going to use 6.63 times 10 to the minus 34 joule seconds. Always use the 6.63 here. Divided by the wavelength is 600 times 10 to the minus 9 meters. Gives us 1.105 times 10 to the minus 27. Or we'll round that to 3 digits, 1.11 times 10 to the minus 27. Hey, what would the units be for this? What would the units be? We haven't talked about that yet. Newton seconds? Who said Newton seconds? Could we use Newton seconds? Sure. That was the unit for momentum, or at least one of the units for momentum that we used in Unit 1 in our momentum unit, right? Sounds a little odd to use Newton seconds here, when we don't even have newtons given to us in this equation, but it works. Okay, Newton seconds works. What else also works? This one sounds even odder. Kilograms meters per second. Remember that one? You don't even have any mass here, but still we can use kilograms meters per second? Yeah, you can. Now, you can actually take the units from this equation as well. You could say joules seconds per meter. Honestly, I'd probably recommend against using that one, only because we're not familiar with that, right? Kilograms meters per second, even though it's kind of odd, works just fine. Just be prepared for whatever. All right, we want to find energy. We've got a couple of options here now. What are my 2 options for finding the energy of this photon? Yeah, what's one? Good. E is equal to P times C. So we can multiply 1.105 times 10 to the minus 27 times the speed of light. What's the other option? E is equal to mc squared? No. No, because we don't have a mass there, right? Guys, listen, let's not overanalyze this. Okay? If you were asked this question a week ago, you'd still be able to answer it. What's the energy of this photon? Patrick? E is equal to hc over lambda, right? We did that before we did the photoelectric effect. E is equal to hc over lambda. So both of them are legitimate. Both of them will give you the correct answer. When we get the answer for energy there, whatever it is, what units should it be in? Joules. And if we're using our standard units throughout, then we're going to get joules for our final answer. All right? Let's take a look at these three questions and see what you can do with these ones. Any issues with those three questions? No? They're all good? Three? Someone say three? Okay, let's take a look at number three. It says if a 10 nanometer photon scattered by an electron becomes an 11 nanometer X-ray, no surprise there, right? The wavelength goes up. Why does the wavelength goes up? Because the energy goes down. Okay, if energy goes down, then frequency goes down, wavelength goes up. How much energy does the electron gain? Listen, we don't need to use the momentum of a photon equation here. We can use E is equal to hc over lambda. That allows us to solve for the first energy. We could also solve for the second energy that way, hc over lambda 2, and then what would we do? Subtract them, right? The change in energy is going to be equal to the final energy minus the initial energy. All right, so we can say 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by the wavelength is 10 times 10 to the minus 9. Okay, do your thing there. Do the same thing over here, except the wavelength is going to be 11 times 10 to the minus 9. Whatever numbers you get there, subtract them, and you should get delta lambda, or delta E, I should say. Now, here's the temptation. Here's the temptation, and this is probably what some of you try to do. You looked at this equation, E is equal to hc over lambda, and you said, well, look, I can find delta E, the change in energy, by just simply saying E is equal to, delta E is equal to hc over delta lambda. Anybody try that? Yes? Doesn't give you the right answer, though, right? Why not? If you were trying to solve for a change in frequency, and you said delta E is equal to h times delta f, that would work. That would work. But this doesn't. Why not? Because it's divided by lambda. Remember, we talked about this one other day. I forget what context, but it has to be a linear relationship. Okay, if you're going to do that, if you're going to change the equation to a delta, then it has to be a linear relationship. You can say delta E is equal to h times delta f. You can't say delta E is equal to hc over delta lambda. You couldn't say delta E is equal to 1/2 m times delta v squared, because that's not a linear relationship either. Does that make sense, guys? If in doubt about something like that, what should you do? This, right? Solve for each of the energies and then subtract them. If you're not sure if you can change the equation, then just don't do it. Solve for the final, solve for the initial, and then subtract them. Here's another one. It says an X-ray photon of wavelength 0.0500 nanometers scatters at an angle of 30 degrees. Calculate the wavelength of the scattered photon. So this is lambda. This would be lambda 1, right? The initial wavelength. Because we do have a final here as well that we're trying to find. We've got an angle here, that's going to be theta, right? Nick, remember we said that theta means the scattering angle of the photon, right? Is that what we have there? Yeah, the X-ray scatters at an angle of 30 degrees. So we're good to go there. Like I said, I'd be surprised if you ever got a question where you're given the angle of the electron. I don't think they'd do that to you. But you could get some kind of qualitative question where you have to distinguish. All right, let's solve for lambda f. Let's get delta lambda first. Delta lambda is h over mc times 1 minus cosine theta. 6.63 times 10 to the minus 34, because we're always using that value now. Divided by the mass of the electron times the speed of light times 1 minus cosine of 30 degrees. Okay, let's do this on our calculator just to make sure that we can do it. What do you think we should probably do first on our calculator, just to avoid a whole bunch of crazy brackets? Do either the whole left part of the question or the whole right part of the question. I was actually going to do the right part first, but it doesn't really matter. I want to say cosine 30 is equal to 0.866. 1 minus cosine 30 is equal to 0.1339. Now I can multiply that by everything that's on the left-hand side, right? So let's multiply that by 6.63 times 10 to the minus 34. And then I can divide that by, let's use some brackets there on the bottom, 9.11 times 10 to the minus 31 times 3 times 10 to the 8. And what do we get? 3.25 times 10 to the minus 13. Let's go a couple more decimal places. 3.250097 times 10 to the minus 13 meters. All right, that's delta lambda. Now, delta lambda we know is also equal to lambda f minus lambda I. We want to find lambda f. Let's just say it's delta lambda plus whatever my initial wavelength was. So it's 3.250097 times 10 to the minus 13 meters plus 0.05 times 10 to the minus 9 meters. Let's add those up. Get 5.03 times 10 to the minus 11. Wait a second, didn't we say the wavelength was going to increase? 10 to the minus 13 to 10 to the minus 11, isn't that decreasing? That's a smaller exponent, isn't it? Did we make a mistake here? No, that's a bigger wavelength, right? It's a smaller number, but 10 to the minus 11 is a bigger, but 10 to the minus 11 is a bigger number than 10 to the minus 13, right? It's closer to 0 than 10 to the minus 13 is. So our wavelength has increased there. So it looks like, it looks like we've probably done this right. Okay, that's a reasonable number at least, right? Any questions about that? The good news is, you get one of these questions, you almost have to be asked to solve for lambda or delta lambda, right? You're not going to be asked to solve for h or mc because those are constants. Could you be asked to solve for theta? Possibly, but not likely. Not likely. Okay. That's the only one that becomes a little bit tricky mathematically, is if you're asked to solve for theta there. Okay, let's try this question, please, on page 724, just the one. All right, if we're good with that one, let's just go through this example. There's no practice problems to go along with this one. We just want to go through this one as a nice little example to show you one more little thing here. It says, what's the maximum change in wavelength that this X-ray can undergo? What's the maximum change in wavelength? This is my initial wavelength. That's all we have, isn't it? That's all we have. Any suggestions there? What equation are you going to use for this? Okay, we don't necessarily know exactly where to go with this question right now, but we do know where to start. Okay, what equation are you going to have to use to find the change in wavelength, whether it's maximum or any other change in wavelength? Delta lambda is equal to h over mc times 1 minus cosine theta. Good. All right. This number, and this number don't change. So you can't change any of those. They're going to have no effect on the maximum delta lambda. The thing that's going to affect what delta lambda is going to be is the scattering angle of the photon. That's it. That's the only thing that can affect what the scattering angle of the photon is. So we don't necessarily want to maximize this angle, But what we do want to do is maximize this number right here. If this number 1 minus cosine theta is really, really big, then delta lambda is really, really big. If this number is really, really small, then delta lambda is smaller. Make sense? All right, how do we maximize that number, 1 minus cosine theta? Okay, good. Look at you. We want the number inside this purple circle to be as big as possible. That means we want this number that's inside this green circle here to be the smallest number possible, right? Okay. If we want, I mean, ultimately, if you're going to subtract that number from 1, we want the smallest number possible right there to get the biggest number possible inside the purple circle. All right, so what's the smallest number possible that we can get from cos theta? We want to minimize cos theta. Let's try 0 degrees. Okay, what's cosine 0? What's cosine 0? 1. All right, 1 minus 1, that doesn't work. Okay, if we go 1 minus 1, then you're going to minimize what's inside that purple circle, right? So that doesn't work. Let's try the next logical number, 90 degrees. Cosine 90 is 0. 1 minus 0 is 1. Okay. So just a sec here. This is going to give us an answer of 0 inside the purple circle there. This is going to give us an answer of 1 inside the purple circle there. So that's a better option, right? That's a better option. What's our next logical angle? 180 degrees. Let's try that. What's cosine 180? Neg 1. Okay, 1 minus neg 1 is? All right, that's even better. What's our next logical one? Probably 270. What's cosine 270? 1 minus 0 is 1. And our next logical one is 360, which 360 is the same as 0, right? So cosine 360 is 1. 1 minus 1 is 0. What's the maximum number that we can have inside that purple circle? It's a 2. And that comes from having an angle of cosine of 180 degrees. So let's say delta lambda max is equal to 6.63 times 10 to the minus 34 divided by 9.11 times 10 to the minus 31 times 3 times 10 to the 8 times 1 minus cosine 180. So effectively what we're going to do there, though, is take that first number, 6.63 divided by 9.11 times 3, and then multiply it by 2. And then whatever we get there is going to be our max change in wavelength. Does that make sense? Let's figure out what that number is, okay? Thank you. We got 4.85 times 10 to the minus 12 meters. So you can get a smaller change in wavelength than that if the scattering angle is different, but you can't get a bigger change in wavelength there. All right, a bigger increase in the wavelength. Good? Easy stuff, right? We could have put this on the test. Okay, we could have tested you on this yesterday. Some questions that I want you to work on here, guys. Page 725. Let's have a look at, let's just go 1 to 5. Let's just go 1 to 5 here. Page 725, number 1 to 5. The photoelectric effect and the Compton effect both supported the particle theory of light. So we've got polarization, diffraction, interference, and refraction all support the wave nature of light. We've got the Compton effect and the photoelectric effect that both support the particle nature of light. Well, let's fast forward a little bit. Talk about a guy named de Broglie. Looks like de Broglie. You call it de Broglie if you want. It's easier to kind of remember that way. But his name's actually pronounced de Broglie, a French guy, de Broglie. De Broglie used kind of a logical argument. Physics is a very symmetrical subject, a very symmetrical discipline. If one thing happens, 9 times out of 10, its complement happens. So it's the opposite to it also happens. If A will cause B, then oftentimes B will cause A, right? Electricity causes magnetism, magnetism causes electricity. Well, De Broglie said, purely a logical argument again here, he had no evidence to support this whatsoever, other than it seems reasonable. He said that if light, which we thought of as a wave, can behave like a particle, then why can't a particle, let's say like an electron, behave like a wave? Again, absolutely no evidence whatsoever at the time in the 1920s to prove that this was correct, that the electron had a wave nature. It was purely a logical argument based on symmetry. He did derive an equation for the wavelength of an electron. You don't need to know that equation. It's a relatively simple equation, but we don't need to know it. But even still, the mathematical equation was kind of abstract. It was kind of just a creation. It wasn't until later on that there was evidence to support the wave nature of particles. That evidence came from electron diffraction experiments. I'm going to show you a video in just a minute here that briefly describes these electron diffraction experiments. What do you need to know about this? If light can behave like a particle, then a particle should be able to behave like a wave, right? If a wave can behave like a particle, then a particle can behave like a wave. We didn't have any evidence to support it until a little bit later on when we did electron diffraction experiments. When we did that, all of a sudden, hey, De Broglie was right. Particles like electrons can have a wave nature. So what are we saying now? Well, not just that light is a wave and a particle, like Einstein said. We're saying that everything's a wave and a particle, right? Not just light, but electrons are waves and particles. Semi-trucks traveling down the road are waves and particles. They have a wave nature and a particle nature. Having said that, a semi-truck traveling down the road, its mass is so ridiculously high that its wave nature is effectively zero. It effectively has no wave nature because it has such a high mass. But when we're dealing with things like electrons, so small, so tiny, it's so minuscule, they actually have a wave nature that they exhibit and that can be observed in certain circumstances. So now we're saying not just the wave-particle duality of light, but the wave-particle duality of everything. This distinction between waves and particles has just gotten fuzzier than it was before.